Hello and welcome to geometry. This is a video over section 1, which is parallel and perpendicular lines. And this is unit 3, and we're talking about angles and lines. So let's go ahead and just get started here, talk about our objectives real quick. We want to be able to construct parallel and perpendicular lines. We want to identify whether lines are parallel, perpendicular, or skew from a three-dimensional figure. And we want to solve problems involving both distance and from a point on a perpendicular bisector to both endpoints of the line segment. So the first thing I want to do is quickly review what kind of lines these are. First of all, this is a pair of parallel lines. Okay, so these are parallel, right? And so the way I know that is because of my arrows here, okay? These arrows indicate that we're parallel. Okay, so arrows indicate that they're parallel. Okay, and this is also another symbol used to show parallel. Okay, this is the symbol for parallel. So I'll often use that, instead of writing out the word parallel. And what we know about parallel lines is that they run side by side and never touch. So run side by side and don't touch, Okay, the next set of lines are perpendicular lines. So we'll call this perpendicular, and these are lines that intersect and form a 90-degree angle. So intersect and form a 90-degree angle, okay? And so what we know, how I can tell from that is usually by this box right here, okay, to show that we're perpendicular. So this is the symbol, okay, this is a symbol for perpendicular, and then there's another symbol for perpendicular, which is the upside down T. So both these are symbols for perpendicular, okay, so this is another symbol, all right, for perpendicular. So, perpendicular and parallel, those are words that kind of take a while to write. And so it's no big deal to actually have symbols for them, but if you see me use the two lines that go side by side like that, that means parallel, and that's what those lines are. And then if you see me use this upside down T, that means that they are perpendicular, okay? So let's go ahead and talk about something here. Let's talk about the shortest distance theorem. And what this theorem suggests is that the shortest distance from a given line to a point not on the line is the length of the segment perpendicular to the line through the point. So what you can do is, if I wanted to find the shortest distance, so, let's just write here the shortest distance from C to line AB, okay, then, that would be a perpendicular line. Okay, so if I drew a line going like this, okay, and said that it was perpendicular, okay, and created a point C, called this point D, CD is the shortest, okay, CD is the shortest line segment, okay? And that's the idea, all right, is that we're just trying to figure that out. So, the shortest distance from line C to AB is a perpendicular line, okay, a line that intersects and makes a 90-degree angle. So you do have to put that symbol in there. If I don't see that symbol in there, then I don't know that it's going to be perpendicular, and I don't know if it's going to be the shortest line. Okay, and you can kind of just think, and if you took, say point C to point A, and then maybe point C to point B, you can just kind of look by these right triangles, that this would be the hypotenuse of the right triangle. This would be another hypotenuse, and so the hypotenuses have to be longer than this side. So the shortest distance would be the perpendicular line. Okay, so now let's take a look at this proof here, and let's prove this. Okay. We want to prove that the shortest distance from C to AB is the length of the line segment perpendicular to AB through that line C. So let's just go ahead and let's just draw an arbitrary line here from C to AB, and I'm just going to put a right angle in there. And once I do that, I'm going to come over here and I'm going to draw my table, and I'm going to put statements and reasons. So statements and reasons, okay? And the first thing that I want to do, it's kind of hard because you're given some information that AB and point C is not on line AB. Okay, that doesn't really tell us much, but let's just say that we come in here and we draw this line, and we'll call this point down here where it intersects point D. Okay, so if we draw a perpendicular line segment, so on my first statement, okay, we're going to draw a perpendicular segment, okay, from C to AB, okay, at point D. Okay, what we call this is the unique line postulate. Okay, and when I say the unique line postulate, basically what I'm doing is I'm just creating lines. Okay, so when I draw that segment in there, I can just do that. Okay, so if I draw a perpendicular segment in there, then that's what we get. Now what I can do is then come over here, and since I've drawn that point, I'm going to draw like another point. Okay, I'm going to draw another line to kind of show you that, and we'll call that point E. Okay, so if I draw that other line CE here, I want to compare CE to CD, all right? And so if I come in here in step 2, I say, draw line CE, okay, that's on line AB, okay? And again, what I'm doing is I'm just creating things. So I'm going to call this the unique line postulate, okay? And so then what I can do is then I can come in here and I can say, all right, well, what do I have here? If I have a perpendicular line and then another segment here, what I have is a right triangle. Now, something we were talking about in the other one, but what I've got here is I can then say that triangle CED is a right triangle. So in my third statement, okay, I would say triangle CED is right, okay? And that's just the definition of a right triangle, okay? Because it has a 90-degree angle. So definition of right triangle, okay? And then what I can then say, what I know about this right triangle is that its hypotenuse has the length of CE, okay? So I'm going to come in here and say that on my fourth statement, and I'm just going to say that CE is the hypotenuse, okay? And what we know about the hypotenuse, and that's just the definition of a hypotenuse. Okay, what we know about the hypotenuse is that it's the longest side. So part 5, okay, then we know we can then conclude that CE is the longest side, okay? And that's just the also the definition of the hypotenuse, okay? So definition of the hypotenuse, all right? And then so what we know is that if I've got these two options here, okay, of having a hypotenuse versus just a perpendicular line, we can then conclude that the perpendicular line is the shortest side. So I'm just going to come in here and then say on step 6 that line CD is the shortest distance. Okay. And that's just the conclusion that we can get from step 5. Okay, that's just the conclusion we get. So conclusion. All right. So kind of a weird proof, not too crazy about it, but I did want to talk about it. You can kind of just get that from up here, but we can also just do the proof down here as well. So the other thing, okay, is the other postulate that we can say is the parallel postulate. And the parallel postulate states that given a line and a point not on that line, so here's a line, here's a point that's not on this line, there exists exactly one line in the same plane that passes through the given point and that is parallel to this line. So there's going to only be one line, okay, and this is the only line through that point that will be parallel, okay? And that's all I got for this, okay? Next page. Okay, we have this thing called skew lines, and skew lines are kind of weird. They are lines that are non-coplanar and do not intersect, okay? In this diagram, what we know is that plane R and plane W are parallel. So it's kind of like thinking of this plane as like the ceiling, and this plane as your floor, okay? And what we know is that C and D, or I'm sorry, DE, line DE is not on the same plane as line FG, okay? And so they're not on the same plane and they're not going to intersect, okay? So we would say that DE is skew to line FG, okay? They're not on the same plane and they're not going to intersect, okay? All right, now on this one, we're given this problem and it says, okay, which are lines that will intersect? So what you have here is you have these two planes, okay? You have one plane and then another plane, and it's like if you had like an X kind of type thing, and they intersect at line D, okay? Now what I know is that line A and line B are on plane M, and then line C is the line that's on plane N, okay? So it says which are lines that will intersect. So what I know is that not only and there's a bunch of different options here. I know that if line C extends out this way, okay, what's going to happen is that eventually it will run into line D, okay? So we can say here that C and D will intersect, okay? You can also make the same claim about line B and line A. We already know that those lines intersect with point D, so we can say, and then the other thing we can say is that if you were to extend out line A would eventually intersect with line B. So we can say C and D and, okay, we should say or lines A, B, and C, okay? And then it says which are perpendicular lines. Now we only have one of those, okay? And that would be line B and line D. And the way that I can tell is because of the symbol that connects them, okay? So that would be line B and D. So B and D. And then it asks, well, which ones are the skew lines? And there's a number of options here, but what I want you to see, the one that you'll probably put down is probably line A and line C, okay? And you could even say line C and line B, okay? Because they're not on the same plane, okay? These lines are on plane M. This line C is on plane N, okay? And they're not coplanar, they're not on the same plane, and they're not going to intersect, okay? They're just, one's going this way, and it's going to go in that way on that plane, and then you have this other plane, and that's where they will intersect, okay? So you could say line C and A, or you could say C and B. Either one would be fine, okay? All right, the next thing we have on our list is the perpendicular bisector theorem, and this is great, okay? And it says that the points on the perpendicular bisector, now let's kind of dissect that for a second. Okay, a perpendicular bisector, we know what perpendicular means. We know that they intersect at 90 degrees. So let's write that, intersect at 90 degrees. Two lines intersect at 90 degrees. And then a bisector is something that cuts it in half. So something that's cut in half. So let's say cut into, and let's do two congruent parts. Okay, it's a little bit more formal. All right, and so what you see here is that you have this line segment QR, okay, and then you have this other line here. Now this line here, okay, is as it's intersected, as this line, basically cuts it in half. So you have these two congruent parts, and it forms a 90-degree angle. Okay, so it cuts it in half and forms a 90-degree angle is the idea. But the thing that we have to understand about this is that if we have points on this perpendicular bisector, okay, any point along this perpendicular bisector is going to be equidistant to the endpoints Q and R. So I'm also going to come in here and I'm going to label this, kind of color this in here, okay, and I'm going to call this is my perpendicular bisector, okay. Now what I'm going to do is I'm going to create, I'll call this QR, I'll call that point S. Let's create a point here, and I'm going to call that point A, okay. And if I were to connect point A to point Q, then I know that that would be equidistant from A to R. And I could say that these two segments are congruent, okay? And so, you know, if AS is a perpendicular bisector, then I know that AQ, what I can then say is that AQ would be then congruent to AR, okay? So any point along this perpendicular bisector would be congruent to its endpoints. You know, I can come in here and I could even do another point, and we'll put this point on here, we'll call this point B, okay? And so, you know, if I were to come in here and do the same thing and say, okay, well, what about, you know, BQ and BR? Okay, these would also be congruent, okay? So if you know you have this scenario where you have a perpendicular bisector, then you know what it's going to be true with those side lengths, okay? You know. All right, then it says, let's take a look at this. Let's do another proof. Okay, it says given that point P is on the perpendicular bisector L, okay, so number one, it tells me that this is a perpendicular bisector. So number one, I see that we have a perpendicular symbol here. However, we do not have the congruent statements for MQ and QN, okay? And we want to prove that PM, okay, is congruent to PN. Okay, so let's come over here. You know, we've kind of we already know that just from the theorem above, okay, but let's actually put that into a formal term, and let's draw our table, and let's write statements, and let's make our reasons. And so the number one statement we have is that P is on the perpendicular bisector L, okay, and that's given to us, okay. And so what we can conclude from that, part two, is we can conclude that MQ, okay, MQ is congruent to QN, okay, and that's the definition of a perpendicular bisector, all right. And then what we have is you know, P is on the perpendicular bisector. I can automatically then say in step 3 that segment PM is congruent to segment PN, okay? And the reason I can say that is because that's the perpendicular bisector theorem. We just said that up here, okay? And so I'm going to come in here and say that that's the perpendicular bisector theorem, okay? And that's it, okay? You don't have to go any further. We're pretty much just done with that. Okay, on the next page, this proof here is the exact same thing that we had before. Okay, given C is a point on the perpendicular bisector L of AB, prove that AC is equal to BC. And that's the same thing we just did. So now I'm just going to answer a couple questions and finish up this video. And it's asking us in this problem here, it says, what is the length of segment AC? Okay, so now what I notice here is you have to look at this picture and you have to say, okay, I have this picture of a line and I have this segment AB. Now, I know that AD is congruent to DB, and it's perpendicular. So I know that L is a perpendicular bisector, okay, which then means that AC is congruent to BC, okay? And I'm going to write that up here real quick, okay? Let me write that AC is congruent to BC, okay, and therefore I can set these two expressions equal to each other. You know, if I want to figure out what AC is, I need to find out what X is, and so I need to set up an equation for that. And so I'm just gonna write 4x minus 5 is equal to 3x plus 2. Okay, and if I subtract 3x from both sides, then I get that x minus 5 is equal to positive 2. So I'm going to add 5 to both sides, and then I get that x is equal to 7. Okay, now I'm not done yet. Okay, I still need to figure out what AC is. And so I know that AC is equal to 4 times x minus 5. So if I plug in 7, I'm going to get 4 times 7 minus 5, which gives me 28 minus 5, which gives me a length of 23. Okay, and that's what AC is equal to, and that's what we try to figure out. Okay, all right, then, okay, it says, what is the length of segment SR? Now, we have a very similar situation here. Okay, we have this picture where I know that these two lines are perpendicular and that RT is congruent to TQ. So L, or this line L, is a perpendicular bisector, which means that any point along line L, like at say point S, is equidistant to the endpoints of the other line segment. So I'm going to come in here and I know that these two segments are congruent. All right, so if I come over here and say that RS is congruent to QS, okay, RS, I can set up an equation and solve these for x. And so I get that RS is 2x plus 8, and I'm going to set that equal to QS, which is 8x minus 4. Okay, and I'm just going to solve this for x. I'm going to subtract 2x from both sides, and that goes away. I get 8 is equal to 6x minus 4. Okay, and then I'm going to add 4 to both sides, and then that's going to give me 12 is equal to 6x. I'm going to divide by 6, and then I get that x is equal to 2. Okay, and so once I have that, okay, we come back. We're trying to find what SR was, all right? And SR had a value of 2x plus 8. So I'm going to come over here. I'm going to write that SR had a value of 2x plus 8. And I want to plug in this 2 in for x over here. So we get SR is equal to 2 times 2 plus 8. So this gives us 4 plus 8. And so we know that SR has a length of 12. Okay, and that's it. All right. Okay, the last thing we need to talk about is the converse of the perpendicular bisector theorem. So it says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. So let's just draw a picture, okay? And if you had a segment here, and we'll call this segment J and then E, and let's say that you had some point up here, and we're just going to eyeball it and say it's right here. We'll call that point O. Wait, get it? J-O-E. Okay, so what we know is that if I have that point O that is equidistant to the endpoints, then what we can figure out, and we know that those are congruent, okay, then I know that O is on the perpendicular bisector, and we can come in here and we can graph that, and we can say, all right, well, there exists this point, and we'll call this point here P. Get it? Joe P. Joe Police. Okay, we know that point O is on the perpendicular bisector, and we can then say that these are congruent, and this forms a right angle. Okay, so you can kind of just draw that picture. So that's it for this page. And that's it for this section. What I want you guys to do is, go ahead and get started on the assignment and get started on the quiz on Edgenuity, and we'll see you soon. Thanks. Bye.